Welcome back to another explainer. I am absolutely thrilled to have you here today because we're about to walk through a mathematical breakthrough that, honestly, it might just reshape the entire future of computing. Now, if you've been following the tech world, you know quantum computing is always hyped as the next big thing, right? But today, we're looking at a specific, concrete tool that researchers just developed to actually turn that potential into reality. It's called the Quantum Hermite Transform. We've taken all the complex research, the data, the articles on this recent development, and distilled the whole shebang down into a visual journey. So get ready because we're going to break down exactly how this new tool could unlock incredibly fast AI and totally supercharge scientific discovery. Okay, let's dive into this by taking a look at the current landscape of the quantum industry. We're seeing explosive growth in quantum hardware. We've got these massive, beautiful, super-cooled quantum computers that are getting more powerful every single year. But there's a glaring issue. We have a severely lagging quantum software ecosystem. The physical machines, they're advancing rapidly, but the software tools needed to actually run complex problems on them, they're falling way, way behind. And without the right software, well, even the absolute most powerful quantum computer is really just an expensive, shiny science project. So here's our roadmap for today's explainer. First, we'll cover the quantum software gap. Second, the quantum Hermite transform itself. Third, compressing complex calculations. Fourth, applications beyond quantum physics. And finally, building the quantum future. All right, let's jump straight into Section 1, the quantum software gap, and why we so desperately need new tools. To understand why this new algorithm is such a massive deal, we first need to establish the core problem holding quantum developers back right now. The big issue in the quantum ecosystem is a lack of what scientists call quantum primitives. Now, a primitive is basically a fundamental computational building block that can be standardized and reused. I want you to think of a quantum primitive like a single, highly specialized Lego brick. In classical computing, software developers have millions of these diverse Lego bricks ready to use, which lets them easily build incredible applications. But in quantum computing, developers are currently working with a tiny, incredibly limited box of Legos. And because that box of quantum Legos is so incredibly small, we run into this major problem, an over-reliance on existing techniques. Right now, researchers lean heavily on a tool called the quantum Fourier transform. Now, don't get me wrong, it's a great tool. But because they lack diverse building blocks, scientists are basically forced to repeatedly use this exact same hammer for every single screw they encounter. They're essentially bottlenecked by this lack of foundational software tools. Which brings us to Section 2, the Quantum Hermite Transform, a brand new quantum circuit. This is the much-anticipated solution that was just presented at the STOC 2026 Symposium in Salt Lake City. And a breakthrough of this magnitude, well, it doesn't just happen in a vacuum, right? Take a look at the incredible powerhouse collaboration behind this algorithm. This project was supported by the U.S. Department of Energy. It actually started with initial discussions between Ning Bo, an assistant professor at Northeastern University who's also at Brookhaven National Laboratory, and Stephen Jordan from Google Quantum AI. This effort then expanded to include researchers from the University of Texas at Austin, so it literally took a village of top-tier academic and corporate minds to crack this mathematical puzzle. So what exactly is the Hermite transform? Well, to understand the quantum version, we first have to look at its classical counterpart. The classical Hermite transform is already a highly vital piece of mathematics. It's used constantly in traditional engineering, physics, and signal processing. In fact, it plays a massive role in describing what's called the quantum harmonic oscillator, which is an absolutely fundamental model in physics. Now, what's really interesting about this is the stark contrasted highlights. You might be wondering, hey, if we already have the classical Hermite transform, why couldn't we just run that on a quantum computer? Well, doing that is computationally expensive and incredibly slow. It just bogs the whole system down. The true breakthrough from this research team was taking that classical math and creating a native quantum Hermite transform. It's a brand new quantum circuit that performs the exact same operation, but does so in a highly efficient, natively quantum way. Moving right along to Section 3, compressing complex calculations, and how this achieves logarithmic overhead. We know this new circuit is highly efficient, but let's look at the fascinating mechanics of exactly how it achieves this incredible speed. The secret sauce here is something called logarithmic computational overhead. I know, that sounds like a bunch of heavy mathematical jargon, but the concept is actually quite beautiful. Essentially, this algorithm drastically shrinks the massive workload typically needed to prepare complex quantum states. Instead of the number of operations growing linearly, where making a problem twice as big requires twice as many steps, the overhead grows logarithmically. This means the algorithm can handle vastly more complex data while barely increasing the computational effort required. It's a real game changer. And this brilliantly illustrates one of the coolest techniques utilized by the researchers to achieve that efficiency, a concept called quantum fast-forwarding. Normally, if you want to compute how a quantum system evolves over time, you have to simulate every single tedious middle step. But with quantum fast-forwarding, you start at the initial state and you quite literally skip the middleman. You jump directly to the future state of the quantum system. It's exactly like watching a movie and skipping straight to the final scene without having to sit through everything in between. And the results of this efficiency absolutely speak for themselves. The researchers noted in their study that this algorithm, and I quote, offers an exponential speed advantage over the best-known classical approaches. Now, when we talk about exponential speed advantages in computing, we aren't talking about something being twice as fast or even 10 times as fast. We're talking about solving problems in mere minutes that might otherwise take classical supercomputers thousands of years to compute. The sheer scale of this speed increase is just staggering. Let's transition to Section 4, Applications Beyond Quantum Physics, and take a look at the real-world impact. So we have this lightning-fast new mathematical tool, but why does this actually matter to you and me? Because, let's be honest, theoretical physics is totally fascinating, but we need to pivot and look at the real-world impacts. The answer lies right here, with Gaussian models. This is the crucial bridge. Remember how we said Hermite functions are used in classical math? Well, those functions fundamentally underpin Gaussian models, and Gaussian models are the absolute backbone of modern statistics, machine learning, and data science. Because this new quantum algorithm speaks the language of Gaussian models natively and efficiently, it directly translates to faster, way more capable artificial intelligence. When you give developers this new, hyper-efficient tool, the industries it transforms are incredibly diverse. This unlocks vast potential for artificial intelligence, obviously. But it doesn't stop there. It opens doors in materials science to discover entirely new alloys, energy research to build better, longer-lasting batteries, and allows for vastly more advanced scientific simulations. It literally gives scientists the power to simulate molecules and chemical reactions with a level of detail that was previously impossible. Finally, let's wrap up with Section 5, Building the Quantum Future and the Long-Term Vision. It's so important to step back and look at the massive long-term vision that this single mathematical foundation represents for the tech industry. So the crucial point is this. The Quantum Hermite Transform is not just a single software app that does one specific thing. It is a reusable tool. It's a brand new, highly powerful Lego block that developers can now use to design entirely new classes of algorithms. The research team emphasizes that expanding this library of primitives is exactly what will ultimately determine what future fault-tolerant quantum systems will actually be capable of accomplishing. As we wrap up today's explainer, I want to leave you with this final, provocative thought to consider. If this single new building block, the Quantum Hermite Transform, has the power to unlock radically faster AI, revolutionize material science, and completely change how we do energy research, what will the next quantum primitive reveal? We're really just starting to fill the quantum toolbox, and the frontier of software is wide open. Thank you so much for joining me on this deep dive. Keep learning, keep exploring, and I'll see you in the next explainer.